thing is what we call integral transforms. You know very well there are lots of integral transforms, but we are going to discuss some very basics like first we will be discussing Laplace transform. So next idea is what we call integral transforms. And what is an integral transform? Let's say you are given a function f of t, and when there is a time domain you always assume that t is greater than or equal to 0, and you are given some another function what we call the kernel of transform. That is something, let's say k, that depends upon t as well as some other parameter, let's say s, and you integrate this thing with respect to t from, let's say, 0 to infinity or minus infinity to infinity, and we call this thing to be, let's say, the integral transform of our function f of t, and this will be a new value. We call it, let's say, capital F, and this will be a function in this variable s. We call this the integral transform, any type of integral transform. We call this function to be the kernel of transform, and this is our function. We integrate from, let's say, 0 to infinity or minus infinity to infinity, and we can write this as the integral transform of our function. And since this integral transform would be a function of s only, so we are going to name it s. Why it is function of s? Because this is a definite integral. You will put the limits for t and you will get only the answer in s. So this is what we call the integral transform. This is the integral transform. This is only valid when this particular integral converges, or what we call it exists. Otherwise we don't say that this particular integral exists. So then we define, okay, for different integral transforms, what is a new thing? Your kernel is going to be different. For Laplace transform, this kernel is going to be e raised to minus st, and for Fourier transform it is going to be e raised to some iota omega x or t, and your limits are going to be different. For some transforms the limit is going to be 0 to infinity, for some transforms it is going to be minus infinity to infinity, and your variable t, it means the dummy variable, is going to be removed because of this limits, and only left is this, the variable which is involved in your kernel. It means the answer is going to be s, and you can name it capital F of s, you can name it f tilde of s, you can name it f hat of s. These are just names. We are not concerned about the names. You can give it any name, it doesn't make any difference. So this is what we call the generalized definition of an integral transform. Now, if you are good enough to introduce your own transform with your own kernel, and your integral transform has some good properties, you can apply it to so many engineering fields, then definitely you are going to get some good reward, because you are going to define your own integral. It must have some good properties and it should be applied in so many engineering fields, then it's okay. There's something going to be a new revelation. So we can define these things, but the thing is that what is the new in your integral transform is going to be very important thing. What is new in your integral transform? So we are going to discuss the same thing.
Kernel is again a function.
So kernel is something, a function of two variables. One is a variable which is involved in your function, another is a new variable. So I will take you 5 to 10 minutes to discuss something that is off topic, then we are going to the topic that we need to discuss. So the first thing that I want to discuss is what we call the natural transform. And let me tell you the good thing about this one. It was introduced by a Pakistani mathematician back in 2008 with the name Zafar Khan. He is, I think, a professor at some university in KPK. So he took the same function f of t, where t is greater than or equal to 0. Then the natural transform of f of t is defined to be integral from 0 to infinity f of something e power minus st and dt. So what is something new in this one? He is not evaluating function on t but on some another parameter ut, and you can see that this is the kernel of the same Laplace transform, we know very well. And the answer is going to be dependent upon two variables. Can you tell me what are those? You can see t is removed in this integration limit. The left is u and s. So we can say it depends upon s and u. Our Laplace transform depends upon only s, but this depends upon s and u. This was introduced by Zafar Khan in 2008 and he named it natural transform. Its lots of properties were then discussed by so many foreign mathematicians, especially Indian mathematicians. But the thing is that why this thing is not something, a new idea, because this thing is similar to the original transforms, only one parameter is different. And if this is used in so many areas with some good results, then this person might have gotten some good awards. But this is not the case right now, because this looks similar to Laplace transform. And when in this you put u is equal to 1, then what happens? In this particular integral, you put u equals 1, then simply you get the Laplace transform of a function f of t, that is 0 to infinity, and f of t e raised to minus st dt. This is simply a function of s. This is the Laplace transform, we know very well. You can find out the Laplace transform of any function by using this integral formula. And this thing comes when you put u is equal to 1. When you put u is equal to 1, this thing happens like that. And what happens when you put s is equal to 1? This is called Laplace transform. Okay, tell me what happens when you put s is equal to 1. This becomes 0 to infinity f of ut and e raised to minus t dt, and this will be, let's say, a function f tilde of u, because you know very well the new thing is u now. And this is another transform, and the name of this transform is Sumudu transform. People call it Sumudu or Sumudu. It is simply the s of f of t, and it is used by so many people in Pakistan to write some new results, to write their research papers, to apply it in their fields of fluid mechanics, and it is used in so many areas. It is called the Sumudu transform. This is the formula, and this is what we know the Laplace transform, and this is the generalized transform, what we call the natural transform. So we will not be discussing anything on this because it's off topic. We will not be discussing anything on this, but people are using Sumudu transforms in so many areas, and they are using some sort of these formulas to solve some equations and so on. We will be discussing only Laplace transform for now. Okay, so let us go ahead with Laplace transform of different functions and its properties. Okay, so then the L of f of t is 0 to infinity e power minus st f of t dt, which is a function of s, is called the Laplace transform of f of t. So this is the definition, and the kernel of Laplace transform is e raised to minus st. This is the kernel of Laplace transform. And one thing we should always keep in our mind, that this is valid when this s is greater than some fixed value, and that value can be 0, that value can be any other value. So we are writing for now s is greater than some c. And in our context, this s is a real number. S is a real number, and when you extend the definition of Laplace transform towards some set of complex numbers, then what happens, the real part of this s should be greater than c. This is the main idea, because we are only doing Laplace transform on the real s, but we can define Laplace transform on some complex s as well. So these are like the restrictions for this one.
What is C there?
C is any fixed, it can be 0, depends upon the integral. We'll be seeing, okay, we are taking one example and we'll see that what happens. Okay, what is the Laplace transform of 0? Laplace transform of, let's say 0. Can we define it? The first thing is that I put there 0, this will become 0, I integrate it, no difference. Laplace transform 0 is 0. It's not defined as it, but we are going to do it so. What is going to be the Laplace transform of 1? You just put here 1, so that's 0 to infinity e raised to minus st and 1 dt, and you are left with 0 to infinity e raised to minus st dt. You just evaluate this integral. Integration is e raised to minus st divided by minus s. The limits are 0 to infinity. Infinity, this is the limit for t, not s. You put t equals infinity here, this becomes 0. 0 minus, you put t equals 0, this becomes e power 0, 1. So 1 over minus s, this becomes 1 over s. And this is only valid when s is greater than 0. Why greater than 0? It is not defined, or it is not clear from this. It is clear from this. When s is going to be greater than 0, then this exponential on infinity will converge. If s is something else up to here, then it will diverge. So 1 over s and s should be greater than 0. Similarly, what is Laplace transform of 2? Not 2, sorry. T. What is Laplace transform of t? You just put here t and you integrate with the help of integrate by parts, and you will see that your answer is going to be 1 over s square. Okay, you can do it easily. And Laplace transform of t square is going to be, I think, 2 over s cube. 2 over s cube. So can we generalize this idea?
Yes.
So in general, what we can write? In general, Laplace transform of t power n is going to be what?
N minus 1 factorial.
If the power of t is 1, the power of s is 2. If the power of t is 2, the power of s is 3. So if the power of t is 1, n, power of s is n plus 1. And the numerator is going to be n factorial. So Laplace transform of t power n is going to be n factorial divided by s power n plus 1. Okay, what is the problem here? That this is valid for when n is going to be a natural number. But can you tell me what is Okay, can I write this thing in this way? Leave it. Laplace transform of t power n is n factorial divided by s power n plus 1. Can I write this thing as this? You know very well n factorial is gamma of
N plus 1.
Can I write this thing in this way?
Sure, sir.
Sure, because now it is only defined when gamma function is defined. For the values when gamma function is not defined, then this thing is not defined as well. So, can you tell me what is now Laplace transform of square root of t?
Not defined.
It should be, because I think it should be.
It should be defined.
It should be.
Something.
So gamma of, because now what's the power of t here? 1 upon 2. You put here 1 upon 2. 1 upon 2
Plus 1.
plus 1 s power 1 upon 2 plus 1. Okay. Now this thing becomes, you know very well, 1 half gamma of 1 half. This thing. Because 1 reduced 1 half gamma of 1 half. And this thing becomes s power 3 by 2. Can I write this thing as this? S square root of s.
This is radical part.
This is square root of pi. So square root of pi 2s square root of. This is the Laplace transform of square root of t. You can evaluate these with the help of gamma function.
I think t power minus 1 over 2 is not defined.
It is defined as well. Yes, it is defined. You want now, let's say in this box we are doing Laplace transform of
Minus
1 over square root of t. That is Laplace transform of t power minus 1 half.
1.
That is simply gamma of minus 1 half plus 1 divided by s power minus 1 half plus 1. This is simply gamma of 1 half divided by s power 1 half. And gamma of 1 half is
Radical.
square root of pi, and s power 1 half is square root of s. You can write as square root of pi over. But the problem is this is not defined. T power minus 1. T power minus 1.
You cover this one.
Because of this, because minus 1 plus 1 is 0, gamma of 0 is undefined. So Laplace transform of t power minus 1 is not defined. Okay, now we got the Laplace transform of some sort of polynomial functions, and now we are going to discuss what is the Laplace transform of, let's say, exponential functions. Okay, so what is the Laplace transform of e raised to at? So you can see that this is 0 to infinity e raised to minus at st e raised to dt, and this can be written as 0 to infinity e power minus s plus a t dt. Just e raised to 18 is written in this form. Now the integral is going to be minus s plus a. Is it okay? No, this should be minus, and this should be minus divided by minus s minus a from 0 to infinity, and you will see that the answer is going to be 1 over s minus a. And this is only valid when s minus a is greater than 0, or simply s is greater than. I was talking about this one. S can be greater than 0, or it can be greater than a fixed value, let's say c. So with the help of this formula, you can find out what is the Laplace transform of e raised to 3t, that is 1 over s minus 3. You can find out the Laplace transform of e raised to minus 3t, that's going to be 1 over s plus 3. We can evaluate these things easily. Okay, the next thing is, what is the Laplace transform of cos, let's say cos at transform of this. And what should be the formula? One thing is that I put cos 80 here, then exponential in cos 80 I have to apply integration by parts twice. It's going to be very difficult. The next thing is that I should write here exponential function, and you know very well the real part of exponential is cos and the imaginary part is sine. I can do that thing as well. But I can do one thing else. I can write just the formula for exponential, that is e raised to I80 plus e raised to minus I80 divided by 2. I can write simply this. We know very well cos 80 is equal to this in the form of imaginary exponentials. Now you apply Laplace transform on these two things separately. Since one thing is that all the integral transforms are linear operators in simple words, are integral transforms. So what does a linear operator do? You can apply it on different parts separately, otherwise you can't do it. And one thing is that we solve differential equations with the help of Laplace transform, with the help of Fourier transform. Those differential equations themselves must be linear. This is the thing. There was a conference at Sakkara. There was a person who was solving an equation. The equation was linear, and he was, I think, using Laplace transform or Sumudu transform that I told you back. So one person asked him that, okay, whether your equation is linear or not. I think he knew it or not, but he mistakenly said it is non-linear. Then he was applying a linear integral transform. Integral transforms are linear. It is not possible. Then the person asked him, okay, if it is non-linear, then you cannot apply integral transforms on that. It should be linear, then you can apply integral transforms. So this is the problem. Either you are unable to apply integral transforms, or your equation is linear. Okay, that's the main thing. So 1 upon 2 is a constant. Laplace transform is linear, integration is linear, differentiation, these are all linear operators. What is the Laplace transform of this? What you need to do, you just write 1 over s minus the coefficient of t, that is iota a, plus 1 over s minus the coefficient of t, that is minus iota a. Done. Just we need to simplify it. 1/2, and this is 1 over s minus iota a, 1 over s plus iota a. You know very well I can take LCM, s plus iota a, s minus iota a, then this becomes s plus iota a plus s minus iota a. Are you okay up to here? Because minus iota a plus iota a cancels, 1 over 2 and 2s, and when you multiply this you will get s square plus a square, and 2 gets cancelled, s over s square plus. This is Laplace transform of cos 80. So you can define it with the help of this, and you just evaluate it, you are done. What is the Laplace transform of sine 80? No, s will be replaced with a upon s square plus a square. Okay. Do you know what are sine and cos hyperbolic functions? What is Laplace transform of 10, by the way? Laplace transform of 10 tangent function.
So first we take replace into sine by cos, then we apply all these transformations. After that one, okay.
It is not defined.
Sure.
Yes. The problem is
Can't we write in the exponential form?
you need f of t to be continuous.
Okay.
Or you can say that f of t to be having finite discontinuities. Finite discontinuities. Because integrals can be defined on finite discontinuities. Your function is going to be this on some interval, then your function is going to be okay. At this point the function is discontinuous and it takes this value. Then at this point the function is discontinuous, it takes this value. But it never explodes. What happens with 10t, you know very well. The graph looks like this.
Okay.
I think at exactly pi by 2 it explodes to infinity. Okay. Then its Laplace transform does not exist. Because it explodes towards positive infinity. That's why you cannot find out the Laplace transform of tangent t. It's not possible. But Laplace transform of sine hyperbolic at is a over s square a square. What is the difference? If this is simply sine at, there is a plus here. If this is sine hyperbolic, there is minus here. Similarly, Laplace transform of cos hyperbolic at is s over s square minus a square. These are some famous Laplace transforms. And now there are some properties for Laplace transform. That's Laplace transform is linear. And what do we mean by linear? That you have a function f1 of t with some coefficient c1, f2 of t with some coefficient c2, and you are finding the Laplace transform of this whole. What you can do, you can first find the Laplace transform of functions f1 and f2. You multiply them with the respective constants and then add. So this is what we call the linearity property. It means you can apply Laplace transform on this first, on the second. If this were not a linear transform, then you can't do this. So this is what we call the linearity property for the Laplace transform.
Linearity shows there. It's your linearity.
Linearity is this definition. Linearity has basically two variants. You can say that if you have something multiplied by some scalar and you apply some linear operator on that, then what you can do, you can apply a linear operator, then you can scale it. The second thing is you have two functions f plus g, you apply a linear operator, then you apply linear operator separately and then add, the answer will be same. This is the, and these two things are merged into this one thing. It's okay to either give this one thing or give these two things separately. And all the differentiation operators, integral operators, these are linear. And there is a whole theory of linear operators that one studies in linear algebra. It is studied in function analysis as well. So
sometimes the definition, the word is written, is continuous and piecewise.
yes, this is what we call the piecewise continuous. It means it is continuous on pieces. It is not continuous on the whole domain, but it is continuous in this piece, then it is continuous in this piece, then it is continuous in this piece. We call this function to be having finite discontinuities. It means this is discontinuous here, here, so it has finite number of discontinuities. So on this particular function we can apply Laplace transform.